Hello everyone. Having learned the concept of the spontaneity, now time has come to define the overall criterion for spontaneity of any given process. In the previous lecture, we have gone through the concept of entropy and the concept of energy in deciding the spontaneity or the feasibility of a chemical reaction. There we have mentioned energy alone cannot decide the feasibility of a chemical reaction, and also the entropy factor or the disorderness or the randomness of the system alone cannot decide the spontaneity of the given system. Now, to decide this spontaneity of any given process or a chemical reaction, now we have to combine these two. A combination of entropy and enthalpy change will decide whether any given process will be feasible or non-feasible. Now, the problem is the combination of these two, the combination of energy factor and the entropy factor to decide the spontaneity of a given reaction. Now, this problem was solved by Gibbs when he introduced a new thermodynamic function, a new thermodynamic state function in extensive quantity which is known as Gibbs free energy. Now, this Gibbs free energy is a combination of the entropy factor and the energy factor, which ultimately can decide the spontaneity of any given process. So we have this term free energy gives free energy. Symbol is capital G. Now this gives free energy. First of all, is a state function. So it means this being a state function, it depends only on the initial and the final state, irrespective of the route taken for the transformation. This gives free energy depends on the mass of the system. So when I say a particular function depends on the mass, so this function depending on the mass or the quantity or the amount, so those quantities which depends on mass or amount, they are known as extensive quantities. So in free energy is an extensive quantity which depends on the quantity. That means if the mass of the substance is more, the free energy will be more. If the mass of the substance is less, the free energy will be less. Extensive quantity. So extensive quantity that can be added or subtracted. So these are additive quantity. They are additive in nature. Now, for any given process, suppose we are having a system is moving from initial state to the final state. Initial state to the final state. So when the system is moving from initial state to the final state, the change in free energy is equals to the free energies of summation of the free energies of the products minus the summation of the free energies of the reactant, if the free energies of reactants and products are given to you. This is for a finite change. For a finite change. Now this free energy for a given chemical process, suppose we have a reactant reactant or reactants is converted into the product or products. So for any given chemical reaction, a reactant is the initial state and the product is the final state. Then this delta G, change in free energy of this reaction, this is defined as the summation of the free energies of the product. This is final, this is initial. Summation of the free energies of the product minus the summation of the free energies of the reactant. So only we are defining the free energies of the product and reactant or the final state and initial state. So this is simply saying this being an state function depends on the initial and the final state. So being an extensive quantity, this can be added or this can be subtracted. So this is gives free energy. Now this being energy, this delta G or G being an energy, the unit of this G, unit is joule per mole. So it has, in sometimes this is defined as kilojoule per mole, etc. Now this delta G or this G mathematically, your mathematical relation, as I told you, this is a combination of energy factor and the entropy factor. So mathematically this G is defined as H plus Ts. So H, this is enthalpy, that is energy factor. This T stands for temperature and this temperature is measured in Kelvin. S for entropy, and this term represents the entropy factor. So combination of this enthalpy factor and entropy factor, this is defined as G, that is free energy of the reaction. So we have this mathematical function free energy, which is a combination of energy and the entropy factor. Sorry, this has to be negative sign. So we have this G is equals to H. H is nothing but enthalpy, which defines the energy factor. Then we have Ts. Ts defines the entropy factor, where S is the entropy, T is the temperature measured in kelvins. Now we have this. So G is equals to H. H is U plus PV. Enthalpy is equals to internal energy plus pressure volume you walk minus Ts. Now therefore change in free energy for a given chemical reaction, this is equals to change in U plus P delta V plus V delta T minus T delta S minus S delta T. Now if the process is carried out at constant temperature and pressure, at constant temperature and the pressure condition, this delta J, what I am trying to convey is this delta J free energy change for any given process, this is defined at constant temperature and pressure condition. So this delta G change in free energy of the reaction, that is at constant temperature and pressure condition. So normally we omit this, but we have to keep in mind delta G is defined at constant temperature and pressure condition. So this equals to delta U at constant pressure. P delta V comes out to be 0. So we have U plus P delta V at constant temperature. Now look at this. Delta T comes out to be 0. So we have minus T delta S. So delta U plus P delta V, this is defined as delta H minus T delta S. So this is the change in free energy for any given process. So change in free energy of the given process is equals to delta H minus T delta S. So this delta H is the enthalpy factor or the energy factor, and this T delta S is the entropy factor. So the combination of these two will decide the value of delta G, and the value of delta G will decide the spontaneity of any given process. So now time has come to define the overall criterion of spontaneity. So next, overall criterion of spontaneity. Overall criterion of spontaneity. For all spontaneous process, now look at this delta G can have three different values. We can have positive, we can have negative, we can have zero value also. So the spontaneity of any given process is decided by the value of this delta G. So we have looked at this delta G. If this change in free energy, which is a combination of H and S, if this delta G is positive, that is greater than 0. When we say delta Z is positive, means the free energies of the product is greater than the free energies of the reactants, because we define this change in free energy as product minus reactant. So when we have delta G positive, means the free energies of product is greater than the free energies of reactant, then the process is non-spontaneous in forward direction, but is spontaneous non-spontaneous in forward direction, but spontaneous in backward direction. So simply we say, if delta G is positive or greater than 0, or delta G summation of free energies of product is greater than the summation of the free energies of reactant, reactant is simply non-spontaneous. So when we use the term non-spontaneous, means we are implying the forward direction or the forward reaction is non-spontaneous. So if the forward is non-spontaneous, then automatically the reverse reaction or the backward reaction has to be spontaneous. Second, look at this. We have this delta G to be negative, meaning thereby this is less than 0. So this signifies free energies of product is less than the free energies of a reactant. So the difference is negative. If the difference is negative, then we say the process is spontaneous in the forward direction. in forward direction but is non-spontaneous in backward. Is non-spontaneous in backward. So the criterion for spontaneity is, then look at this. For any process to be spontaneous, then the free energy change for the process should be less than zero. That is, the free energy change should always be positive for every process. When the free energies are decreased, then we say the process becomes spontaneous. And all naturally occurring irreversible process, for all those irreversible naturally occurring process, delta G is found to be negative. So this simply means if a process is to be spontaneous, rather than seeing the energy factor and entropy factor alone, we have to combine these two, and the combination which gives the free energy change should always be negative. Any process in which there is a decrease in free energy is always spontaneous in the forward direction. If the reaction is spontaneous in the forward direction, the backward shift or the reverse shift will always be non-spontaneous. Then the third quantity possibilities is delta G can also be 0. If delta G is equals to 0, it means the free energies of product is equals to the free energies of reactant. If the change in free energy for any given process is 0, we say the reaction is at equilibrium. So at equilibrium, the free energy change will always be 0. And the free energy change positive, spontaneous in the forward direction, free energy positive, non-spontaneous in the forward direction. So this is what we call as ultimate criterion or the overall criterion for deciding the spontaneity or the feasibility of any given process, whether the process is physical or a chemical process. Now this value of delta Z depends on enthalpy and the entropy factor. So we have this delta H and delta S. So ultimately look at this, delta S value and delta H will also decide the criterion of spontaneity. That is what we call as temperature dependence of spontaneity. How spontaneity of a given reaction depends on the temperature of the reaction. Now we are coming to that particular point. On varying the temperature, how the spontaneity of the reaction can be changed, or how can a non-spontaneous reaction can be converted into a spontaneous process, and how a spontaneous process can be converted into a non-spontaneous process by changing the temperature of the reaction. So that one thing that we have to keep in mind is delta G, we are measuring the change in free energy of the state. So this is the free energy of the system, and this delta H is enthalpy of the system, and this delta S, this is also the entropy change of the system. This is for the system. What is happening inside the system we are carrying out, and that defines the values and system. So this is for system, this is also for system, then this is also for the system. We are not dealing what is happening outside the system, we are dealing in what is happening inside the system. So coming to the temperature, effect of temperature on spontaneity. Effect of temperature on spontaneity. Now for this, we have to see the value of delta H, delta S and the temperature, and how this delta G varies with temperature. We have this delta S, we have this delta S, then the value of delta G, then we have a remark here. Now the first case, if delta H is negative, delta H negative means we are having exothermic reaction. A reaction is exothermic, and this delta S is positive means there is increase in entropy of the system. If delta H is negative, delta S is positive, then delta G will always be negative. We have this relationship, delta G is equals to delta H minus T delta S. So look at this, delta S is positive, so positive, we have a negative, so this term comes out to be negative. Delta H is negative, so negative plus negative, this is always a negative, so delta G comes out to be negative. So if reaction is exothermic followed by increase in entropy, then there will always be decrease in free energy. Delta G will always be positive, and the reaction is spontaneous at all temperatures. Whether the reaction is carried out at low temperature or high temperature, reaction will always be spontaneous, provided delta H is negative, delta S is positive. Take the second case, delta H is positive, means we have endothermic reaction. Reaction is endothermic and there is decrease in the free energy. So delta H positive, delta S negative. So look at this, delta S is negative, so negative into negative, this comes out to be positive. Delta H is positive, so positive plus positive, delta G will always be positive. So if delta H is positive, delta S is positive, then delta G will always be positive. This is non-spontaneous at all temperatures. These type of reaction can never be meant to be a spontaneous reaction. So endothermic followed by decrease in entropy. The forward reaction will always be non-spontaneous at any given temperature. Whether you increase the temperature or decrease the temperature, reaction can never be spontaneous in the forward direction. But the reaction will always be spontaneous in the reverse direction. Then coming to the third, now we have look at this, delta H is negative. There is decrease in energy, that is exothermic. Simultaneously there is decrease in entropy. Entropy also decreases, enthalpy also decreases. Now we have cases here. Now if this is the case, then delta G, for this case, delta G can be negative or delta G can be positive. Now look at this, how this can be positive or negative. We have a delta H which is negative, delta S is negative, so this comes out to be positive term, this is a negative term. So we have a summation of negative and positive. So if the negative value is greater than positive value, then delta G will be negative. So negative value greater than positive means these temperatures should be low. If reaction is carried out at low temperature, the value of this T delta S will be less than the value of delta S. So ultimately delta G comes out to be negative. So delta G negative means at low temperatures. So when the reaction is carried out at low temperature, this T delta S, that is the positive quantity, is less than the negative quantity, so the difference comes out to be negative, and delta G negative means the reaction is spontaneous. So for this reaction is spontaneous at low temperature. That means for such type of reaction, when there is a decrease in enthalpy and decrease in entropy, all such reactions should be carried out at low temperature so that the forward reaction is spontaneous. But if the reaction is carried out at higher temperature, look at this. If temperature is high, so this positive term T delta S, because delta S is negative, so this comes to be a positive. The positive term will be greater than the negative term, so the ultimate summation will be a positive. So this positive is at high temperature condition. So when the reaction is carried out at high temperature condition, delta G will be positive. If delta G is positive, then the forward is non-spontaneous. So this type of reaction is non-spontaneous at high temperature. So the condition is, for such type of reaction to make the spontaneity, the reaction must be carried out at low temperature. If the reaction is carried out at high temperature, then the reaction becomes non-spontaneous. This is non-spontaneous at high temperature. Then we have the fourth case. Delta H is positive. Delta S is also positive. There is increase in energy of the system, that is endothermic. Along with this increase in energy, there is increase in the entropy. Again, now for this we have two cases here. Delta G may be negative and may be positive. So delta H is positive, delta S is negative, positive. So this term comes out to be negative, this term is positive. So again we have a summation of positive term and negative term. If the positive term is less than negative term, this term comes out to be negative in this case. If the negative term is greater than the positive term, then delta G will be negative. So for this negative term to be greater than the positive term, the value of temperature should be high. So for this reaction, delta G is negative at high temperature. That means, look at this, for such type of reaction, endothermic followed by increase in entropy, the reaction should always be carried at high temperature so that delta G comes out to be negative. So these types of reaction is spontaneous at high temperature condition. If high temperature is spontaneous, then the low temperature will become non-spontaneous in the forward direction. So this delta G comes out to be positive if this negative term is less than the positive term. So negative term less than positive term will be possible if only we have low temperature condition. So delta T should be low. So at low temperature, when the reaction is non-spontaneous at low temperature. So means, look at this, if the reaction is exothermic and there is increase in entropy, that is spontaneous at all temperature because delta G is always negative. If the reaction is endothermic and there is a decrease in entropy, delta G is always positive at all temperature conditions, so reaction cannot be made spontaneous. If delta G, the reaction is exothermic, that is followed by decrease in entropy, then reaction to be spontaneous, reaction is to be carried at low temperature. At low temperature condition, delta G is negative, so reaction becomes spontaneous. At high temperature, the same reaction changes to a non-spontaneous reaction. If the reaction is endothermic followed by increase in entropy, then the reaction can be made spontaneous at high temperature, and at low temperature reaction is non-spontaneous. So this is what is the effect of temperature on spontaneity, or how this non-spontaneous, the effect of temperature can be made on these two cases. So in these two cases, we can vary the temperature. By varying the temperature, the reaction can be spontaneous or reaction can be made to be a non-spontaneous reaction. So for this, we have to be very careful in deciding the value. So ultimately deciding factor is this delta G. So delta G should be negative for any process or any given chemical reaction to be spontaneous. This is the overall criterion for spontaneity of a given chemical process. Then we have a term standard free energy. Sometimes we use this standard free energy. Standard free energy. So when you use the term standard free energy, that is G naught. This naught represents standard state. So standard free energy means the standard condition. What is the standard condition? Standard condition, temperature is 25 degrees centigrade, that is 298 Kelvin. If we have a gas, then pressure is at 1 atm for gas. If we have a solution, then the concentration of the solution is again 1 molar. So this condition is what we call a standard. So under this standard condition, the entropy change, free energy change will be standard free energy change. So therefore look at this, delta G standard is equals to the summation of standard free energies of product minus the summation of free energies of the reactant. Or look at this, delta G naught is equals to delta H naught standard enthalpy change minus T delta S naught standard entropy change. So this is standard condition, to temperature automatically fixed at 298 Kelvin. Then we also have standard free energy of formation, that is standard free energy of formation. So look at this standard free energy of formation, that is G standard F. So standard free energy of formation is defined as the formation of a particular substance from its elemental state under standard conditions of 25 degrees centigrade, pressure being 1 atm and concentration being 1 molar. So this is free energy of formation. Free energy of formation of 1 mole substance, free energy of formation of 1 mole substance from elements under standard condition. This is defined as standard free energy of formation. So therefore this delta G naught F is equals to summation of standard free energies of formation of products minus summation of standard free energies of formation of reactant. So this standard free energy change can also be related to equilibrium constants. Now just don't ask me what is equilibrium constant, that we will discuss in the next chapter, that is equilibrium. So since this thermodynamic quantity can also be related to equilibrium constant, so I am just giving the equation, and by use of this equation we can solve the problem. So standard free energy change and the equilibrium constant. Equilibrium constant is known as KEQ. So the relation is delta G is equals to minus 2.303 RT logarithm of K equilibrium, that is the equilibrium constant. R is a gas constant whose value should be taken as 8.314 joule per Kelvin per mole. T is temperature measured in terms of Kelvin scale, and this G must be joule per mole. So if you look at this, delta G naught is equal to minus 2.303 RT log equilibrium. This is the relation between equilibrium constant and delta G standard free energy change. Now look at this. From this equation we come to the conclusion, if K equilibrium is greater than 1, if this K equilibrium is greater than 1, logarithm of something greater than 1 is always positive. So this term comes out to be negative. Delta G naught will always be less than 0, negative होगा. If K equilibrium is greater than 1, logarithm of something greater than 1 is positive. So right hand side term comes out to be negative. So delta G is less than 0 or negative. If K equilibrium is less than 1, logarithm of something less than 1 is negative. So negative into negative, the right hand side comes out to be positive. So delta G is greater than 0 or positive. If K equilibrium is equals to 1, equilibrium constant is 1, so logarithm of 1 is 0, so right hand side comes out to be 0, therefore delta G naught will be 0. So this is how we relate equilibrium constant and the free energy change under standard condition. So under standard condition, delta G free energy change is equals to minus 2.303 log K. So from this we can define the value of equilibrium constant. So look at this, how to find equilibrium constant from this. So we have looked at this, logarithm of K equilibrium will be equals to minus delta G naught divided by 2.303 RT, or we say take this anti-log, then we say this is K equilibrium is equals to 10 to the power minus delta G naught divided by 2.303 RT, that is what we call as NT. So we'll find this value first. We can easily predict because this is standard condition. Temperature is for us 298, R is a constant. We have this value, so we can define this value. Once we define this value, we have to take the anti-logarithm. So anti-logarithm means of log K, that is K equilibrium is equals to anti-log of this value. So this simply means this is anti-log of minus delta G naught divided by 2.303 RT, that is K equilibrium. This is how we define equilibrium constant from free energy change. So simply now look at this, looking all these factors, we come to the conclusion that this delta G is the ultimate criterion for deciding the spontaneity of any given process. Whether the process will be spontaneous or non-spontaneous, this is always defined by this term, that is free energy change, which is a combination of enthalpy and the entropy term. Now look at this problem. We have a problem. We have given a chemical reaction. Hydrogen gas combines with oxygen gas to give you liquid water. Now question is, find the standard free energy change for this reaction provided enthalpy change is given, entropy is given. So we have this relationship, delta G naught is equals to delta H naught minus T delta S All the question says this is under standard condition, so temperature comes out to be 25 degree, that is 298 Kelvin. So this is minus 571 minus 298 into minus 326. So this is minus 571 plus this term 298 into 326. Now look at this. This is joule, this is kilojoule. So we have to convert this in terms of kilojoule. Or we can convert this into kilo image. So now look at this. If you look at this is minus 571. This is 10 power minus 3. Obviously, so this is less than 1. So delta G comes out to be negative. So we say this reaction is spontaneous. Reaction is occurring under spontaneous condition. So this is how we comment on the nature of the reaction, whether the reaction will be spontaneous or non-spontaneous. Now we have the second reaction. Nitrogen gas combined with oxygen gas to give you NO gas, for which the enthalpy change under standard condition is given as 89.96 kilojoule. Standard enthalpies of NO, oxygen gas and nitrogenous are given to you. Question says find the standard free energy change. So we have this relation. Standard free energy change is equals to standard enthalpy change minus T delta S standard condition. We have this delta H, we have this T. Now we have to find this standard delta S. So therefore look at this. Standard delta S is equals to summation of standard enthalpies of the product minus the summation of standard enthalpies of the reactants. So look at these products we have NO to standard enthalpy of entropy of NO minus standard entropies of reactant, that is half of entropy of nitrogen plus half of standard entropy of oxygen. So from this we define standard entropy change, because these values are given to you, we have a given value. So first we have to find the change in entropy from the reactant and the product's value, and we use this value here in this equation to find the values of standard free energy change for the process. Now we have a given chemical reaction. For this reaction, enthalpy and entropies are given. Question says at what temperature this reaction becomes spontaneous. Now question says temperature at which the reaction becomes spontaneous. So we have to find the temperature at which the reaction will be spontaneous. So to define spontaneity, we have to find the value of delta G. So once we have this delta G, then that value should be negative. So for this delta G to be negative, once we have this delta G negative, then that value should be the value at which temperature should be negative. Spontaneous. So we have this delta G naught is equals to delta H naught minus T delta S. Now we have delta H here, we have the delta H is positive, delta H is also positive, so we have a positive, we have a negative. Now for this delta G to be negative, this difference should be negative. That means for spontaneous, delta G should be less than 0. So for this delta S to be less than 0, this term delta H minus T delta H should be less than 0. But for this to be less than 0, then this term should also be less than 0. So if this is less than 0, means delta H delta H naught, and this T minus delta S. So for this, look at this T delta S naught should be greater than delta H, or we say this T delta H naught should be greater than delta H naught, or we say this temperature should be greater than delta H naught by delta S naught. Delta H naught is 131.3 kilojoule per mole divided by 0.1335. Again, this is kilojoule, so this is Kelvin per mole. This is Kelvin. So any temperature greater than this value, the reaction will always be spontaneous. So look at this. What we are using is, for spontaneity, this delta G should be less than 0. For this to be less than 0, the right hand side should also be less than 0. Means this difference should be less than 0. For this to be less than 0, this term, T delta S term, should be greater than delta S. That means temperature should be greater than this ratio. If temperature is greater than this ratio, then reaction will be spontaneous. This is how we correlate spontaneity with delta G. We have this reaction with hydrogen gas combined with iodine gas to give you HI gas. In standard free energy of formation of HI is 1.3 kilojoule per mole. Question says, find the standard free energy change for this reaction. So we have this. So standard free energy change, we have a given chemical reaction, so we say this is standard free energy of formation of product minus standard free energy of formation of reactants. So formation of product means we have this, so 2 into free energy of formation of HI minus free energies of formation of hydrogen gas plus free energies of formation of iodine. So this is 2 into 1.3 kilojoule per mole minus standard free energy of formation of elements in their most stable state is always 0 plus 0. So therefore this is 2.6 kilojoule per mole. So standard free energy of formation of elements is always 0. So that's the reason why standard free energy of formation of hydrogen and iodine were never mentioned. So please keep this thing in mind. Standard free energies of formation of elements is always considered to be 0. So next question says, we have an equilibrium reaction. Acid plus alcohol gives you ester plus water. That is an equilibrium reaction. For this equilibrium reaction, question says the equilibrium constant is 4 at 25 degrees centigrade. What is the equilibrium free energy change? Standard free energy change. So we have this relationship. Standard free energy change is equal to minus 2.303 RT logarithm of K equilibrium. So we have all these values. Minus 2.303, R is 8.314, temperature is 298 Kelvin. So we have 298 into logarithm of 4. So this is minus 2.303 into 8.314 into 298. Log 4 is log 2 square. So this is minus 2 into 2.303 into 8.314 into 298. Log 2 is 0.301. So this is, so from this equilibrium constant we are finding. Now look at this. This delta G is negative, so reaction is spontaneous. If you ask to comment on the nature of the reaction, so delta G being, so look at this, K equilibrium is a greater than 1. So K equilibrium greater than 1 is log of something greater than 1 is positive. So this delta G comes out to be negative. So reaction is spontaneous in the forward reaction. So this esterification reaction takes place spontaneously at a given temperature. So the next part is, question says the delta G naught for an equilibrium reaction is minus 20 kilojoule per mole. Calculate the equilibrium constant for the reaction at 25 degree. Again, same question. So same formula will be used. So delta G naught is equals to minus 2.303 RT log K equilibrium. So look at this, delta G is minus 20 into 10 to the power 3, that is kilojoule, is equals to minus 2.303 into 8.314 into 298 log K equilibrium. So negative will cancel out. So therefore log K equilibrium is equals to 20,000 divided by 2.303 into 8.314 into 298. So therefore K equilibrium will be equals to anti-log of this value. So look at this, delta G is negative, so K equilibrium should be greater than 1. So this is how we define equilibrium constant from standard free energy change or standard free energy change from equilibrium constant. So this, by use of this, we can define the equilibrium constant also. So this is the ultimate value which we are going to use to defining the spontaneity of any given thermodynamical process, whether the process is physical or whether the process is chemical. So this is all about the second law of thermodynamics, which decides the ultimate criterion for spontaneity of a reaction. So to decide this, we take the help of energy and entropy. Combination of this develops into a third physical quantity, that is standard free energy change, and this free energy change decides the criterion for the reaction. So for any process to be spontaneous, this free energy change should be less than 0 or should be negative. Then there is a statement already that I have mentioned while discussing entropy, that is third law of thermodynamics. So third law of thermodynamics statement says, for a perfectly crystalline substance, so I am using the word, for a perfectly crystalline substance at 0 Kelvin, the entropy is always 0. So perfectly crystalline means highly ordered, this orderness is 0. And that too at 0 Kelvin, when the thermal motion of all the components is ceased. So at that point, for a perfectly crystalline substance at 0 Kelvin, the entropy will always be 0. That is 100% perfect. That is 100% order. This orderness or randomness is 0. That is simply the statement of third law of thermodynamics. So just keep in this mind. So all my dear friends, colleagues and their students, this is all about thermodynamics.